I'm going to talk about Anthony's industrial science, in particular the work he did at Schlumberger Cambridge Research and across Schlumberger over very many years. We're talking about a period of about 30 years. And this, of course, covers a huge range of different technologies and science in which he was involved. And I was very fortunate that I joined Schlumberger and the Research Centre at the beginning of that period, and Anthony was one of the first people I met. So let me just go to the next slide. Okay. In the middle here, you can see a picture of the Research Centre in Cambridge. It was a very unique design, and it's actually designed correctly as a scientific research centre because underneath those big bubbles there are large-scale experiments. And in fact, Anthony had a big hand working with a man called Bernard Vivet in designing this centre and actually setting out the ethos of the whole centre and recruiting the scientists into the centre. So this building didn't exist when Anthony joined the company, and he was part of the actual the people who actually determined how it should be put together. And below you can see a picture of some of the people who started the centre. Bernard Vivet in the middle there, Anthony alongside. One person is missing from this group who was, because this picture was taken a bit after the centre had got going, was a man called Les Bradbury. And Les actually recruited me. Les was really an experimentalist and an aeronautical engineer. And Anthony, of course, is a theoretician. And I was hugely fortunate to have the two halves of the equation, as it were, together, to be led by Les to always look at the different types of experiments that might be performed, and with Anthony to help me see my way through some of the mathematics. And just as an illustration, there is a picture of Anthony and me looking slightly different with a little more hair. And I see on the wall there, we have a Venturi for some reason, and I can't actually remember ever working particularly on Venturis, so I suspect it was for the photo that we were scribbling that up. But actually, it's a good reflection of the fact that Anthony and I spent many hours together talking about different parts of the science that was going on at the lab. I've been in and out of this lab here for the best part of 30 years. I spent about half my time elsewhere in the world. But what did Anthony bring to the lab here and to the 100 PhD scientists who work in this lab? I think the first one was scientific rigor. And it made it quite an exceptional place compared to many other labs that he set a hugely high standard for the science. Many of you, or all of you, don't have access to the scientific report archive here in the lab. And those reports are of quality that could be published anywhere in the world. And it's really up to, due to Anthony, that that's the case. The other thing he brought was a fantastic breadth of knowledge across many different parts of fluid mechanics and beyond fluid mechanics. And I think for a young lab with young scientists in, that was important because we were relatively narrow when we started. He has a very natural style of mentoring. He actually just helps you think things through, think the problems through, and helps you find your way into new parts of science. One of the things I think Anthony got from his time in the Journal of Fluid Mechanics was that he read all the reports that were being produced. And he would come back with comments and corrections and new thoughts on pretty much everything. And he kept on doing that throughout his whole time in the lab. And I think it's really quite remarkable. 100 scientists put out a lot of paperwork, and he really kept up with everything that was going on. As has been said by some others, scrutiny of scientific thought. He really instilled the scientific process into the scientists who came and joined, the young scientists. He's renowned for his challenging style in presentations. And in fact, one of the topics I chose today is because I actually remember the moment I presented a particular graph, which I'm going to present a similar one today, and his response. I can even remember the room I was standing and where he was sitting. Such was the discussion that followed. And I have to say, finally, he's always been enormously generous with his time. And as a scientist, I found him really fantastic to work with. And later, when I was managing this organization here and across the whole of the research for Schlumberger, he always came in and gave me extremely good advice and help. I'm going to talk about two problems, and they're from that time where I was with Anthony and the others here at the lab. And the first problem is when you want to make a hole in the ground safe, and you want to make a high integrity pressure seal. So you've made a deep hole in the ground, and you might want to do that for oil and gas wells, but increasingly in the future we'll be doing it for geothermal wells and for CO2 sequestration, both of which, by the way, have their own particular challenges, which in some senses can be more challenging than the first oil and gas wells. So what do? You have a hole in the ground and you put a cylinder into the hole, it's called a casing, and the cylinder has a radius which is about 80% of the radius of the hole. And what you do is you're going to fill up the gap between the cylinder and the rock around the cylinder with cement and let the cement set, and that's going to make the hole safe. And the classical way in which this is done is that prior to introducing the cement slurry, which is not a slurry like you would see on a building site, it's rather a more sophisticated fluid with many different additives and some elastic components as well, and increasingly very much a designer fluid. Before you introduce that, you circulate whatever fluid is in the well hole around first. And you do that because the fluid that's initially there has some thixotropy, and so you actually modify its behavior and its response by actually making sure it's been sheared. Then there's you push the cement into the hole, and you do so down through the tubing. We'll come back to why that is in a second. And in order to separate out what the relatively lighter green fluid from the heavy cement, you have a bung, a rubber bung in between the two of them. And as that travels down to the bottom and that bung reaches the bottom, it bursts. And then the cement comes up the annulus around the casing, the tubing, and fills the annulus. And it displaces the original fluid that was in the hole. And then following the cement, you pump another fluid, the green fluid again, and there's another bung which comes along, which allows you to determine when you've reached the end of the job, because when that bung hits the bottom, the pressure at the top of the well goes up and you know you've finished. So at the end, you end up with a fluid inside the well, and you end up with the cement around the edge and the annulus. So why do you do it in this form? It's because the cement and the green fluid have different densities, and when you're doing this displacement up the annulus, you have a heavier fluid below the lighter fluid. The characteristics of this operation are actually about 50% of these operations take place in laminar operations and 50% in turbulent operations. And we have here a narrow annulus. And I just want to point out the aspect ratio here. We're 3,000 meters down typically, and we might have a hole which is about 0.3 meters across. So a huge aspect ratio. And we started to try and solve this problem and understand what to do to make this work efficiently and always correctly. And in laminar calculations or laminar predictions and experiments, we realized that this lubrication approximation would again rear its ugly head. And we were able to form a mathematical model which actually was pretty reasonable for predicting the laminar operations. In turbulent flow, we scratched our head, and Anthony proposed that we have a little look at some Taylor dispersion. And I'm going to talk a little bit now about the Taylor dispersion. On this slide, we now have a crash course in Taylor dispersion, a one-slide crash course, and actually it's relatively simple, although I haven't seen too many papers where it's written out cleanly. And here I've got a XYZ axis, and of course the Z axis is much longer than the horizontal. And what we're going to do is we're going to just see how a tracer is going to disperse up the annulus. And to do that, we're going to have an advection diffusion equation, and we're going to assume we know what the velocity field is, which is going to be independent of time and is going to be axial just up the annulus. And it's just going to be a function of X and Y. And we're going to see how this concentration is going to evolve. And Taylor originally did his analysis for tubes, and you can do it for slots and other things. We're going to do it for an annulus. And I didn't non-dimensionalize this. Unfortunately, Anthony's on mute, so he can't complain about that at the moment. But I feel it's just a bit easier to see this quickly if we keep it dimensional. So we have a small parameter, which is h upon L. And what we're going to do is we're going to move with the mean velocity of the fluid and change our axial scale to Z to reflect that. And also we're going to look at long distances, so we're going to put an epsilon there. And we're going to look at very long times, and we're going to put an epsilon squared there. And we've popped that into the advection diffusion equation, and we get this new advection diffusion equation. And then the grad squared with the right angle at the bottom is just means in the plane. And we just do a simple regular perturbation, and we end up with some equations for C0, C1, and C2. And you can pretty quickly see that the C0 equation is going to tell us that C0 is going to be a function of Z and T only. And this is our 0th order moment, and we're interested to know how this is going to evolve in time. From the C1 equation, we quickly find out that the solution for C1 is separable, and it's going to be separable into a function in the cross-section and then to a derivative of the C0 function. We still don't know what that is yet, but that's how it's separable. And just notice the 1 upon d creeps in there. The C2 equation we integrate across the cross-section, and now we can see what that looks like. We see that there's a diffusion term axially, and we have this next term which has a dc1 by dz, and because d0 by dz, we can see that's going to turn out to be a diffusion term. So we pop those things back together, and we see we have a diffusion equation when we're moving with the mean velocity. And very peculiarly, we have a k upon d squared, which says that the smaller the whatever that diffusion is, the bigger the dispersion will be. And what is this function g? Well, this function g has to satisfy a Poisson equation, which is shown at the bottom, where it's driven by this difference of the velocity to the mean velocity. It's got Neumann boundary conditions and a 0 mean. And this number k here, which is 1 upon 48 for a tube, is just calculated by doing the mean of the functions w minus w bar and g. So it's a product of two functions which both have 0 means, but their product does not have a 0 mean. So that's it, that's how you get there. And D, what is D here? Well, D for a laminar flow would be molecular diffusion, but in turbulent flow, it might be a turbulent diffusivity. So we'll come back and talk about what D might be in reality. That's the end of the crash course. I unfortunately lost any notes on this, and last week realized I would have to reproduce it at rather quick notice. And fortunately nowadays, I did have a finite element package, which is free FEM on my computer. And also very fortunately, some people have done a lot of nice work on different types of fluids, and particular fluids with yield stresses, in particular Glowinski. And there's some nice modern numerical methods for mixed numerical methods to solve those problems. And I was going to look at turbulent flow, but let's have a look at laminar flow first. And this is the plot that gave me a little bit of grief in a presentation to Anthony some years back. So we're going to look at an eccentric annulus, and we're going to look at Newtonian, and then I thought we might have a look at a Bingham plastic. So an offset of 0 here is a concentric annulus, and an offset of 1 means the inner tube is touching the outer tube. And K here is that number K up in that effective diffusivity, and we're very interested to know the size of K. And first of all, look at the Newtonian result, which is really quite remarkable. I've rescaled this graph. I should have put it on the y-axis, but I've rescaled it to the concentric case for the Newtonian solution. For a slot, it's 1 upon 210. 1/210th is the solution. And here, we've rescaled it to be 1 for a concentric annulus. And you can see, as we excenter the annulus, it goes up by a factor of 300 or 350. That is hugely remarkable. And when you look at the flow field, you can see it's very skewed to the wide side of the annulus. And that is what is causing this massive dispersion in the long time limit. And in fact, as you increase K, the time taken to reach that limit also increases. And so one can imagine you might not even reach the Taylor limit by the time you get to the top of a well, if it's purely laminar. And now the second one is Bingham plastic. This is a Bingham plastic with a relatively high yield stress. And that has the unusual behavior of having a solid lump on the uniform, no shear region on the wide side, and actually can go completely still on the narrow side. And again, I'm happy that everyone's mute, because somebody might point out that the diffusion coefficient in the non-shearing region is going to probably be 0. And so how can you take a Taylor limit? And that's a very interesting question, and I'm just going to come back to that on the next slides. But this is, really quite a big effect. So really, I think the discussion is how can we make these operations work well? And the dominant term here is actually this k upon d squared. So what we'd like to do is either minimize k or maximize d. And so minimal dispersion is maximum d. And of course, in turbulent displacement, you get a turbulent diffusivity that goes a long way to helping to increase d. Ian Sobey did some very nice calculations, and you can see some on the right in slots of multiple Newtonian fluids. And on the left hand of those pictures, you can see a heavy fluid displacing a lighter fluid displacing a heavier fluid. So the top interface on the left is stable, whilst the bottom interface has a big tongue going through it. So that's going to cause a lot of mixing. And then on the right-hand side, this one, I believe, has different viscosities as well as densities. And you can see a big mixing zone being created as a result. And so that's a good thing, because the more that we increase D, the smaller the dispersion is going to be for these problems. I was well aware also that rotation increases in plane mixing. And here at the bottom, you can see some calculations for a Bingham fluid and an eccentric annulus with rotation. And I just wanted to point out one rather neat thing here is that if you follow a particle path, it whizzes around the center tube. And as it whizzes around the center tube, it goes through the plug flow on the wide side of the annulus, which is slightly rotated. And so it has zero shear whilst it goes through there, and then comes back out and then is going through a shear region. So it's got this helical path where at one point it's going through zero shear. Very neat, really. And so if you were to do a tailored calculation for this, you would have to have zero diffusion in that point where there's a plug flow, and then you would have a non-zero diffusion coefficient elsewhere. And I think that would still end up at a Taylor limit to be proved, I think. So there's a competition between the eccentricity and the rotation, and Ron Smith did a very nice JFM paper where he showed that competition for a narrow eccentric annulus for a Newtonian fluid, and showed how much you have to rotate the center body in order to get rid of this or reduce this dispersion. And by the way, it's quite possible to rotate the center bodies, and it's a very good way to improve these type of operations. So that was my first example. I think it's quite fascinating in a way. So I'm going to move on to the second example now. And this is sand transport in a fracture. And I think we'll hear a bit more about this when we get to Emmanuel's talk, but from a geomechanics point of view. So of course, there's applications in conventional oil and gas wells, and also in geothermal wells for hot rock. You get some fracturing events there. I exclude from this unconventional shales, which is all the rage in North America now, because they actually more rubberize the local formations than cause this sort of fracture. So in classical fracturing, what you do is you get actually a very clean fracture generally, and it can be 100 meters long, might be 30 meters high, and just a couple of centimeters across. And what you do is you pump a clear fluid into this to start fracturing the rock. And then you have a high sand loading, maybe as much as 40 to 50%. And you pump that in after the clear fluid, and you want to fill up that slot with the high sand loaded fluid. And so you get gravity currents. You also get fluid leaking off into the formation either side of the slot. Fluids are generally non-Newtonian, actually viscoelastic quite often. We get gravity currents. We also have, of course, sedimentation going on. And if the bed builds up at the bottom of this fracture, then this operation will fail, and it does fail sometimes, just as, by the way, the previous example can also fail. And lo and behold, how to approach this is, again, a lubrication approximation. And in fact, the discussions here are less on the lubrication approximation that we had, but more on the sedimentation phenomena. So I'll start with the lubrication approximation. So the way to do this, or we did this, was we said that we're going to have just a tracer which we're going to follow, and we're going to let the fluid properties be function of the concentration C. It's in fact the concentration of sand particles C. And so we're going to have density and viscosity and other properties as a function, and yield stresses, for instance, a function of this concentration. And we're going to introduce some hindered settling of particles, and we're going to come back to this relationship where the particles are going to slip relative to the fluid. So what you do is you take the Navier-Stokes, you apply a lubrication approximation because the width is very small compared to the height or length. I'm going to call the non-dimensional gap width h, which is going to be a function of position along the fracture and vertically upwards. And if we integrate the continuity equation, we just have to allow a little bit for the fluid leak off, and that's VL in that first equation. Across the gap, the leading order term is that the pressure is constant across the gap, so it's just a function of x and z and t I should have in there. And then the other two equations I haven't integrated across the gap. And mu here would of course be, it's a non-dimensional viscosity, would be a constant for a Newtonian fluid, but for a non-Newtonian fluid, the second and last equations are coupled, and you cannot solve them at this point because you need to know the concentration of sand across the gap in order to solve that coupled pair of equations. And so the transport of the sand is given by the last equation, and there's a little effect here at the end for the fluid leak off. And now we make an assumption because we want to make progress, and we assume that the particle distribution is uniform across the gap. I'll come back to that in a second. And as soon as you can do that, you can begin to integrate those second and fourth equations together. And you can then separate out that averaging on that transport equation. So having done that, we can then introduce a stream function, which is a little bit modified compared to normal with a leak-off contribution. And we find that we can end up with an elliptic equation. And in fact, if you can remember Paul Hammond's talk this morning, you will have remembered he had a 1 upon h cubed sitting in there at one point. Well, this is again a similar result for this lubrication approximation. We have a buoyancy term with a buoyancy driven flow with a buoyancy number of b, which has it's a non-dimensional number. Mu is a non-dimensional viscosity here. And we also have a leak-off term. And this is coupled with the transport equation. And then when you do the non-Newtonian version, it's a little bit more complicated. You get some more complicated functions under that left-hand operator. And you have some auxiliary equations in order to work out what that function actually is. However, so this is the lubrication approximation for that particular problem. So what happens is, well, these fractures are not, vertically, they're not just square, they're sort of oval when they're formed. And we're going to pump in from the left-hand side a high sand-laden fluid into following a clear fluid. We're not going to look at the evolution of the fracture itself, but what's going to happen is the fluid is going to preferentially go along the halfway up the fracture because of the shape of the fracture. And it zooms along the middle, but of course we've got sedimentation going on. And the sand sediments down, so this is showing you the sand sedimenting down, and it builds up a packed bed. And that concentration equation actually admits discontinuities in the sand concentration, so you have to solve it reasonably carefully. It's a bit like a compressible flow in that sense. And as you go along and pump more, you see the sand bed building up, you see the sand-laden fluid coming in, and this can then go wrong. I think you can imagine it can go wrong. And this is an example of things going wrong, and that bed of sand is just building up fast back to the well bore and actually stops the operation. So the question is, how does this actually function in reality? And there's a problem, and this is the problem which Anthony and I discussed, a number of these different things here. And this is the settling speed of the sand relative to Stokes settling of a single particle. And you can see on the left-hand axis, we've got from a tenth to 1 times the Stokes settling up to 100 times the Stokes settling. And there are so many effects going on here. For instance, we're pumping a cold fluid into a hot formation. So the fluid near the boundaries will be hotter than the core fluid. And so you'll get mixed convection, and you expect that to increase the sedimentation, overall sedimentation rate. If you have a very high concentration of sand, however, you get hindered settling, which reduces the rate of sedimentation. And very unfortunately, sitting here is the boycott effect, which is first found for separating out blood corpuscles from blood. and you put it in a tube and you incline the tube. And you only have to incline a tube a few degrees, a long tube, a few degrees to get this effect. And it increases the overall sedimentation enormously. And there's no reason whatsoever not to expect these fractures to have an inclination to the vertical. And that's not easy to predict and is pretty much unknown. And when you look at this diagram, you come to the conclusion that it's very likely impossible to predict this phenomena accurately, given the unknowns of the situation. Unfortunately, despite all the nice lubrication approximation, I'm not sure it's really a useful calculation. So I just wanted to come to a conclusion here. So one quick conclusion is that one I just mentioned, that there's insufficient information to predict the outcome of that operation, in my view anyway. And then I wanted just to say a few more words about the general conclusions. I mean, what's very noticeable, just for instance, in that last problem, is there are a broad range of fluid mechanics phenomena going on. And you need somebody like Anthony about to really steer you in the right directions and to make sure you take into account those aspects of the problem which are relevant and important. And I think that really needs a lot of experience to see those complexities. And I would almost call it an art because it really relies on having seen a very large range of solutions in fluid mechanics. And of course, you have to do all of this whilst reducing it to tractable formulations which can actually be used in practice. And I think Anthony always steered everybody in that direction based on his very good experience, both in academia and in business. So happy birthday, Anthony, and thank you very much for all the guidance and help you gave me at that time.